Okay, welcome back, everybody. We've got about 50% of us back. Everyone else is outside enjoying the weather, but I'm sure they'll come in. So we will get started on time, try to keep things going. And I think we're kind of shifting now to the data provider perspective and see some examples of how different groups have managed their need for fair data and redistribution of data. So that with Ken, talking about Biogeochemical-Argo.
Okay, great, thank you. You may not think of Biogeochemical-Argo as a time series site. The world is my site. Okay, so Biogeochemical-Argo, fair data. I like to say fair, findable, accessible, interoperable, reusable, and reliable. We have fairer data. Okay. This is the current state of the Biogeochemical-Argo array. Been funded by a whole slew of federal agencies. I want to acknowledge the data team at MBARI. So on this slide, the yellow dots are the floats that we process at MBARI. The biogeochemical floats is something like 70% of the array, led by Tanya Maurer. Nicola Geist-White is not here, but she will be.
She will be.
Coming. And so real quick outline, just a little few words about Biogeochemical-Argo. Our data system structure is international, highly documented, kind of fits in anyway. And our data is freely available in real time. The goal is really to have the data available within quality control, properly flagged and available within 24 hours of it being transmitted from the float. They are pushing us to get it down to 3 hours. Okay, I'm not sure we can do that. And then a few words about the data is findable. People are doing science with it. If you haven't seen a float, that's what a float looks like. I didn't show in this plot, but floats, they profile typically every 10 days from 2 kilometers depth to the surface, collect data, phone home by iridium, and this is what one float time series might look like. There's 5 years of data from a float. This float has batteries for about 7 years, so it'll run a couple more years after this. It's gone across the polar front a couple of times. So you see temperature, salinity, POC, particulate organic carbon, is actually inferred from optical backscatter. Think of that's just the optical backscatter. Chlorophyll A, from chlorophyll fluorescence, oxygen, saturation in this case, nitrate, pH, and you see that float is tracked, most of the way across the Indian Ocean, which is kind of a terrible way to do a time series for floats that go across the Indian Ocean, right? That's a little awkward. And so really the power of Biogeochemical-Argo is to do global to basin scale science. Lower right is the oxygen at 300 meters from all the GLODAP data that took 50 years to accumulate all that data. Panel above that is the same kind of a map, 300 meters oxygen data in the year 2024. We can do it in a year. And the panel on the left is the oxygen at 300 meters last month. Okay, we can do that monthly. You can actually do it every 10 days. You want to break it down, you can do 3 of those a month. Okay, and the data is of very high quality, I would argue. We put a lot of effort into ourselves trying to ascertain the quality of the data. We put a lot of effort into then fixing the problems. And so one of the points is this data set is always evolving in time. So we will find a new algorithm, we'll reprocess the data, we'll correct for errors that we know in the data. But we put a lot of effort into doing each of these plots is like float oxygen versus bottle oxygen map ups from hydrocasts near floats for oxygen, nitrate, and pH. And the offsets are small. For oxygen, it's 1 micromolar. For nitrate, it's 0.4 micromolar. For pH, it's 0.008 bias. Pretty good. But don't take our word for it. Other people, this has become a cottage industry of taking the data and independently trying to find the biases in it. This is so the float oxygen data is going into World Ocean Atlas now. If you want to look at the change over time and merge the ship data and the float data, it's super important to understand if there are biases. And in this case, if we compare, this is a histogram of float oxygen minus ship data. The offset is 1.4 micromolar, okay? That's a big deal. 1.4 micromolar, if you want to look at a change in time in the ocean, super important. We have to understand this control for it. It's especially important if you look at this histogram on the far side. Red this is the number of profiles in World Ocean Database for oxygen that go below 900 meters, 1,000 meters. If you want to know about oxygen in the open ocean, red used to be all ships. Nobody goes on ships anymore and collects data and at least puts it in the database. It just doesn't, it's not a thing, right? The blue are the ship CTD oxygens. Those are also decreasing. And what is now become the dominant source of global oxygen data by about a factor of compared to the current state from ships by a factor of 10, profiling floats. It is our dominant data source, but we have to put huge amounts of effort into understanding biases. And there are half a dozen papers out. There is a small bias. We're working to remove that. You may go download the data. The bias is in it this month. Next month, the bias is gone. That's the kind of thing. It's a living data set. So there are monthly snapshots of the data every month with the DOI. You can take all of the data each month if you want. It's about 10 gigabytes. Download it and you have a reference for the data you analyze. Somebody else comes along and says, oh, the bias that you saw last month is gone this month. You can start to understand why. It's also documented how the data was reprocessed. The metadata tells you what was done to fix the data. The data system is quite international. There are about 20 countries deploying BGC floats. There are 11 international, there's not one data center, there are 11 international data centers that process BGC data. Hence, it has to be highly documented so that we can keep the data, reasonably homogeneous across all of the data centers. So 11 data centers, and then 2 global data centers. So the float operators send their data to the local their national data center. That data gets processed, then sent to the global, their redundant 2 global data centers that that's where you would go to get the data. Nicola will talk more about this and show some of the tools to do that. There are also 5 regional centers that don't really focus so much on processing the data, but on the science and the array, the actual mechanics of the array. Do we have enough floats? Where should they go? And so on. And altogether, 34 nations, although some of those nations just put out temperature salinity floats, about 20 do things. And so what we run at MBARI is essentially a sub of one of the national data centers that focuses on just BGC, okay? So our data system interoperates to process the BGC data. We interoperate with a variety of other data streams. So we are getting data not just from the floats, but from CCHDO, the Carbon and Climate Hydrographic Data Office at Scripps, from CBAS, NASA's data system, from NCEI, the National Centers for Environmental Information. We assimilate the GLODAP data as part of our quality control process to compare our data sort of to the historical highs and lows of nearby GLODAP data. To calibrate oxygen, we need to know atmospheric pressure. So sometimes we either get it from NCEP or from ERA reanalysis systems. And we put the data on the GTS, the Global Telecommunications System run by the World Meteorological Organization for real-time assimilation by operational data centers. Okay, so I won't take a half an hour to walk you through the whole scheme here, but data comes from the floats, goes to our partners at Scripps, UW, Woods Hole. MBARI processes the data. We don't operate the floats. Those are our partners, Scripps, Woods Hole, UW. Synchronizes to MBARI. We then process the float raw voltages and spectral data into concentrations for nitrate pH. We do in a real-time data adjustments and validation that assimilates data from GLODAP and so on to adjust to quality control the data to understand if it's within specifications, and then create a variety of data products which are distributed through a whole set of online mechanisms. But the important point is that at Argo, that data is monthly rolled up into a tarball of all of the data at that point in time, given a DOI and made available. And you can go back and get the data from July of 2022 if you want, or whatever. So you can, whatever you download, you can you can specify. And I just wanted this reference down at the bottom, Maurer et al. 2021, delayed blood quality control is a great paper that explains really how all this works. But as I said, there are 11 other data centers running this, so the process is beyond a nice peer-reviewed paper. There must be like 1,000 pages of documentation on, this was for a talk I gave about at MBARI about our program, and so these are most of the technical documents we've written, but there are a fleet of other ones that other people have written. Processing BGC-Argo nitrate, quality control manual for nitrate and pH and so on. So those are all available online at www.argodatamgt.org. And so the data is findable, it's accessible, it's reusable. Hundreds of papers, I think there are close to 700 papers having been written with BGC-Argo data in highest profile journals, all kinds of interesting science. Just to make the point, it's interoperable. Here's a paper where they take the satellite estimates of particulate carbon, use the float vertical profiles of particulate carbon, and make a series of maps from the surface down into the mesopelagic of POC at the resolution of a satellite, but using the float to give you the vertical attenuation of the profiles. So interoperating with satellites. Here's an example where we've merged, not me, but other users have merged the ship data with the float data, and here's the time series of the oxygen anomaly, essentially the mean oxygen and the mean oxygen, and then each yearly value oxygen decreasing in time based on profiling float data time series globally of the oxygen decrease at different depths, 0 to 100 decibar, and then 600 to 2000 decibar, and so on. Nice paper, Maslow float and the ship and float pH values merged. You can make a nice map then of surface pH, but this lower left panel shows the rate of pH, the pH trend per decade, a zonal section across the Southern Ocean with the different polar zones, the seasonal ice zone, the Antarctic zone, polar frontal zone, subantarctic zone, subtropical zone, showing that the changes in pH that you observe, it makes sense in terms of the global overturning circulation. That's merged ship and float data. On the right is the paper we're working on now, but you can just take the 10 years of float data. It takes about 10 years, the pH signal is emerging, and you can get a statistically significant pH signal at various locations now around the world ocean. Huge benefits from the BGC data in interacting with the time series site data. This is a paper that I wrote with Mariana Biff, just looking at global primary productivity by diagnosing the diel cycle of oxygen in the surface ocean, which you can get from the floats. Although they cycle every 10 days, you can get the hourly change in global oxygen from the floats. And we compare our rates with essentially gross oxygen productivity with the values. There's little green squares on that map where there are enough profiles to figure this out near hot or near bats. And we get rates that agree quite nicely with the profiles at hot and bats. But this is from the global float array. So huge value in using the time series sites to validate. Did I run out of time already? No.
Got a minute?
Got a minute? Okay. I'm about done. These are now floats. Their time series sites may benefit from the really higher resolution of the float array. This is nitrate, but from 8 years of data, floats near Hawaii. This is what I get if I download the Hawaii data, gridded at the same resolution. You just see, and this was a paper we wrote in Nature, showing that a very high frequency events. It's not, nitrate is not this smooth blob, but there's just lots of up and downs. And if you have lots of floats, you start to see. And so I will just say, stay tuned for tutorials on how to access the data and visualize it. We happen to love Ocean Data View. So you can get it all. There is an online web ODD, Ocean Data, BGC-Argo data set, and you can make plots. Thank you.
Perfect time.
It's wonderful. So good to see so much data for the public. There are some plans or at least discussions about incorporating new measurements, especially for biological parameter imaging. So what are those plans?
So there's that, it's a very, very structured system. There is a task team that is dedicated to bringing new, evaluating. So there's a whole protocol to bring new measurements into Argo. You're thinking of the UVP, the underwater vision profiler, kind of it's so super interesting science. If you want the value, all the real value of it, you've got to get your float back, which is not an Argo kind of thing. We put them in the water. We're talking about this. How liberating it is to put stuff in the water and not expect to get it back, not to have to worry about whether your mooring is going to come back. I love that. But the UVP, you want to get it back, and so there, anyway, there's a whole international protocol to bringing new things into Argo. You don't just say, I've got a iron sensor and bolt it on the floats and declare victory and go on. You've got to get it approved. So there, yeah. UVP is it's got some momentum. I don't know quite where it falls because it's a little more complicated than a normal thing.
Just there is data, imaging data,
Well, that, I mean, the problem really is the volume of the data, and you have to start doing it's the whole story about data compression and kind of above my pay grade on that. But it's beautiful data. I get it.
All right, thank you. We are going to move on to Raquel. She's going to talk to us a little bit about OceanSITES, another kind of global scale data aggregation distribution site. So go ahead, Raquel. She's virtual, by the way, if you can.
Hi, well, good afternoon to everybody. We were introduced before, so you already know my name. And as I said, I will give some slides for examples from OceanSITES. So I want to start like thanking not only Heather, but also the rest of the METS committee for organizing the workshop, and also to OceanSITES executive committee and the DMT, because well, the progress of achieving FAIR included in these slides is really the results of OceanSITES community working together on this. So let's see if it's working. Okay, so let me introduce what is OceanSITES for those of you. I think there will be people in the room that maybe is not very familiarized with GOOS Global Networks. So GOOS is the Global Ocean Observing System, depending on the International Intergovernmental Oceanographic Commission of UNESCO, and has the mission to grow an integrated, responsive and sustained observing system for which GOOS works together, among others, with the Global Ocean Observing Networks as OceanSITES. So then OceanSITES sits parallel to other global ocean observing networks, such as Argo, but also DBCP, Ocean Gliders, GoShip. And OceanSITES specifically is the global network with the mission to coordinate the collection, delivery, and promotion of the use of high quality from long-term, high-frequency, multidisciplinary observation at fixed location in the open ocean, not only from moor time series, as you see a sketch in the slide, but also from sea-based time series, as we will see during the presentation. So this fact is not the only fact that OceanSITES share with METS, but they have also some more commonalities and difference with other GOOS networks. So when one says global, as for example, in comparison with we see that when we are talking about OceanSITES or METS, we are not referring to a global coverage aim, but that the network is the sum of efforts of national Eulerian observatories for global needs. So global ocean climate records, as we all know, are built little by little through the contribution and integration of distributed and heterogeneous long-term fixed time series collected by a small team of researchers. So OceanSITES is established as METS out of the need of coordination of these efforts on long-time series observation for global good, and is operated by the community for the community with the vision to advance towards this interoperable, fair, multidisciplinary ocean climate records that enable users deriving information on climate change, on ocean forecasts, and ocean health. So as a very quick summary, OceanSITES has more than 376 sites, is measuring more than 20 essential climate variables and essential ocean variables, not only physical, but also on biogeochemistry and biology. For example, like oxygen, particulate organic matter, inorganic carbon, variables related to phytoplankton or zooplankton, as we will see now. So how is OceanSITES progress on achieving FAIR? So let's say that making the data findable and accessible, one can consider that is the easy part. So initially, OceanSITES was designed with a centralized data scheme in which OceanSITES data can be found, let's say, in a one-stop shop, the global assembly centers at IFREMER and NOAA, where data from different sites can be found. So this approach has worked for a long time. It was mentioned at the beginning this morning that things are changing in the web, and OceanSITES is also trying to make efforts to make changes on this direction, because as I said, because this is the sum of efforts at national levels, it must be recognized that at some nations, it is mandatory that the data are provided at some specific repositories. And in that sense, it has no sense that PIs are putting data in different repositories. So OceanSITES is trying to progress from this centralized data management system to a fair distributed database. But this is true that this is not a trivial task, but in any case, OceanSITES data are findable and available. So what about interoperability? So how the data, so previously in the GDEX and in the GDEX from different sites provided by different research teams and nations are has this interoperability because, as it was also explained this morning, they share a common and a standard format. And this is the result of the strong data management system in OceanSITES that is based on the monthly meeting of the data management team, in which all the metadata, the standard names, the quality control, all the vocabulary, all the metadata that should be related with the different variables that are included in NetCDF OceanSITES data format are discussed. So, and then as a sum of this effort, this OceanSITES data reference manual is explaining all this content. This manual is continuously updated and revised. And in fact, through this revision and updating, it has been endorsed as an ocean best practice by GOOS. And I see, maybe you see that the quality control and uncertainties, I already mentioned that this is a very important point for making the data reusable. That is the next point. Why? Because including this quality control and the uncertainties of the different data is mandatory for OceanSITES data. And knowledge about this quality control and uncertainties is what we think really enables that the data could be used or reduced for different applications. To know which is the uncertainty related with the data will allow you to discern which application it will enable to you. So we have seen that which is not always indicated, not only for OceanSITES, but also for other ocean data, is the method, let's say, behind obtaining these uncertainties or this precision. This is not always indicated in the data, and this is something that we would like to be working, on in the future. So we not only work on data, we also work in ocean best practice. We also share codes, and we also share software. And so examples of this I will provide in the next slides for different variables. So here you see some recommendation for ecological variables on moorings, but we can find this also for specific variables like oxygen. You see like compilation of, as it was mentioned during presentation this morning, what makes interoperability and reusability is this work together in a community, like trying to find which is the best way for a community to do something. And so these are examples of works on this community perspective for oxygen, for example, from moorings. And so the ways to calibrate in comparison with this CTD and Winkler determination here are also included, for example, the comparison with Argo floats. And this is something that is different from Argo, the fact that these platforms are always recovered from the sea. So we always have access to pre-calibration and post-calibration and calibration in between, which gives this high quality, let's say, to the data. We know which is the quality that we have at any moment. Regarding this metadata, you can see here example of how are all the content of the general information about a site and a time series. I think it's very small, but maybe you can see that for oxygen, for example, in a time series, you have information about the sensors, about each slope calibration of the sensor regarding to the Winkler determination at that moment, about the uncorrected and corrected version of the data. There are also examples for examples for particulate or particle fluxes. Some from different sites. As I said, it's a community work, so we can find work contributing from SOTS in Australia, PAP. I listened that it is all, there is someone also in Bermuda from the representing the time series, and also like examples of the data, the information that this data, this type of data requires in NetCDF data format. We are aware that this standard of data is maybe not very, let's say, friendly for people working on more ecological data. And so I think workshops like these ones are opportunity for the communities to work together and probably find a way to implement in this kind of format the the agreements that will be achieved during the workshop to be included in this type of format, or communicate the different type of data. Finally, I wanted to give you some examples of software share. For example, it was mentioned also during the Argo presentation, net community production. So net community production can also be obtained from Moore time series. We can calculate air-sea fluxes with the atmosphere for oxygen and then calculate the residual of oxygen that remains, that then belongs to the biological activity. And this type of code is shared, and we can apply to different sites, and we can make this comparison of the net community production and primary production also using like algorithms typically for satellite measurements, but from Moore time series, and also compare this estimation with primary production estimates directly from the, let's say, incubation from the SIP time series. And finally, another example of biological estimate that you can, for example, obtain from Moore time series is from backscatter from ADCP. You can estimate the biomass of zooplankton. And this is an example of the type of data that you need to be providing for giving this backscatter from ADCP. And that's all from my side. Thank you very much.
Thanks. I'll come up there so we don't have time. But so more for comment, and you know, it sounds critical, but this is a workshop, and we do have to do the systems that work ultimately. I mean, it's really great work, but remember the sort of perspective initially that I think these are sort of questions of Argo and OceanSITES getting their houses in order, right? The FAIR principles, you have to be a little bit careful, because findability, yes, you're findable to people who know where to look and how to look. That's changing again. Argo Viz is putting Argo records into Otis, so they're generically findable. So Google, Microsoft, UNESCO, others can find it. I think what we need to do as a community sort of like elevate what Danny presented this morning, the sub-principles of FAIR. So if you're accessible, if you have NetCDF files, you're not complying with sub-principle A2, because the metadata and data are packaged in the same thing, and if the data disappears, so does the metadata. So these are great steps, it's fantastic things, and it's that getting one's house in order. But we have to be now focused on that next step of FAIR, the implementation step, because I don't think a lot of these things are fair in the context that we're actually working in. But it's easy to get there because of this work that has been done. But all of that internal documentation, etc., is getting us to the house in order stage, but not to the project to the world stage. Doable entirely, I guess that's why we're here. But I'll put that in there because again, we must also identify what is not working.
I think that's a great point. I think of it as kind of the changing landscape, you know, nothing is stable, and something that was looking really good in 2007 is not quite compatible.
Well,
with
maybe, but you know, the web has been stable for a while, and none of this stuff is available on the web yet. Some of it is now. So it's not that it's like a continually moving target. It's that we developed in isolation.